Welcome. In this video, we are going to look at limits and continuity in two or more variables. Before we jump into derivatives, we must first establish what a derivative is, and like we did in Calc 1. But don't worry, we're not going to be doing any epsilon delta proofs right now. Recall from Calculus 1, we had this function f of x be defined for all x not equal to a in an open interval containing a. L is a real number. Then the limit as x approaches a if f of x is equal to a, f of x is equal to L, the number L. For every epsilon greater than 0, there must exist a delta greater than 0, so that the absolute value of x minus a is less than delta, which is obviously bigger than 0 because it's an absolute value, for all x in the domain of f. Then f of x minus L is going to be greater than some epsilon. Now, we're going to then consider what does this look like in 3 space. 2 space, we had some interval that had that x value in it. In 3 space, what we have is a disk delta. So similar to what we did before, we have some disk delta so that we have x minus a squared plus y minus b squared is less than some epsilon squared because these are both squared. And now we're looking at a disk, which of course, when you think about a disk, it's basically just a circle. And this disk has a radius of delta. So this is what it would look like. It would look something like this, where here is the point that we're interested in and our value x that we're approaching a. And the disk is, or the value of the output, my epsilon, must be contained within this disk. So what does that mean for us? Well, then when we're looking at the limits, the limit as f of xy, as xy approaches some ab is going to be L, and it's written as this form. The limit as xy approaches a and b, x approaching a, y approaching b, of f xy is equal to L. For every epsilon greater than 0, there must exist a delta greater than 0 so that all the xy are in that disk around the point AB, except for possibly AB itself. What that means is, as before in Calculus 1, we don't necessarily have to have it defined at this moment for the point that we are looking at. Before, remember in Calc 1, when we first explored limits, it didn't necessarily have to be defined at that point A. And now in 2 space, we don't have to necessarily have it defined at AB for the limit to exist. Okay. So if we take a look at what this looks in 3 space. So here's our disk. We get an L that is within the neighborhood of L plus epsilon and L minus epsilon, and here's the disk. That means our point AB must be within this disk. Our delta has a radius. Our delta is the radius of our disk centered at AB. Now, again, it doesn't necessarily have to be defined there. We get some limit laws like we did in Calculus 1. First limit law is that the limit of a constant is a constant. The limit as I approach x, as I just approach just x, is going to be the a. As I approach just y, it's going to be y. So the limit as xy approaches ab of just y is b. And the limit as xy approaches ab of just x is going to be a. We're going to get the sum laws, which means if I have these 2 functions in terms of x and y, it is going to be what each one does individually. So I can take the limit of each one individually. Same thing with the subtraction. I can subtract each one individually, which would be the limit, assuming the limit as xy approaches ab of f of x is L, and g, the limit as xy approaches ab of g of xy is m. I can add the limit, I can subtract the limit. Of course, we have the constant as a constant multiplier. And again, we have the multiplication here, so that's nothing surprising. We also have the division, and we have the power, which of course then gives us the root. So let's go ahead and evaluate the limits, and if they do not exist, state they do not exist and explain why. So the first thing is, like we did in Calculus 1, is we determine whether or not we can just do by a direct evaluation, by a direct substitution. So if I put in 0 for x and y, I don't have a restricted 0 divided by 0, so I can just do the direct substitution. The limit laws that allow me to do this is the limit as xy approaches 0, 0 of the numerator, so 4x squared plus 10y squared plus 4, divided by the limit as xy approaches 0 of 4x squared minus 10y squared plus 6. And it's a direct substitution. And what allowed me to do this is my quotient law. So I can take the limit of each one individually. And when I do that, I'm going to end up with 4 in the numerator and 6 in the denominator, which of course reduces to 2/3. So that is my answer. Now let's take a look at my next example. I have the limit as xy approaches 4 of e raised to the negative x squared minus y raised minus, it's e raised to the negative x squared minus y squared. Again, we can just do a direct substitution here. So we have e raised to the negative 4 squared minus 4 squared is going to give me e raised to the negative 16 minus 16 more, which gives me e raised to the next 64. C is a little bit different. I can't do a direct substitution yet, because if I try to do a direct substitution in the denominator, what ends up happening is I end up trying to divide by 0. So I can't do a direct substitution. So what I am going to do is I'm going to look at just this piece of it and say, hey, that kind of looks like the difference of squares, but more like a difference of squares, but in 2 variables instead of just 1. If I think about that a minus b squared, a squared minus b squared is a minus b, a plus b. And if you remember in pre-calculus and calculus 1, when I had, hey, if I had x minus 4, I can still factor this like the difference of squares, square root of x minus 2 and the square root of x plus 2. So I'm going to do something similar to that in my numerator here, is I'm going to use those rules and say, hey, if I group this as x minus y minus 1, and I factor it as the square root of x minus 1, x minus y minus 1, multiplied by the square root of x minus y plus 1, difference of squares, then I will have some cancellation in the denominator, and I can just do a direct substitution. So I have the limit as xy approaches 2, 1 of the numerator, which is x minus y underneath the square root minus 1, multiplied by the square root of x minus y plus 1, divided by the square root of x minus y minus 1. And then we have a nice cancellation here. With that nice cancellation, we can do a direct substitution. We are now at the limit as xy approaches 2, 1 of the square root of x minus y. I went wild on my square root there. And then plus 1, which gives me, with a direct substitution, 2 minus 1, the square root, plus 1, which gives me an answer of just 2. We're going to do something similar with D. We're going to do the factoring. Now we know that the numerator is the difference of cubes. So this becomes the limit as xy approaches 0, 0. Again, we're doing this because I can't do a direct substitution in my denominator. It's going to be x minus y, and then it's going to be x squared plus xy plus y squared over the x minus y. And again, these will cancel. And I can do a direct substitution, and so I just end up with 0 as my final answer. So can we do this with 3 or more variables? And the answer is yes. So our epsilon and our delta is going to change slightly. We went from a delta, which is an interval, to a delta that's a disk, which in 3 space or higher means that our delta is a ball. So we're literally having a ball. So here's a definition for doing the limit on our x, y, and z. Notice that we have our x minus x naught squared, y minus y naught plus z minus z naught squared is less than epsilon. We have a ball, and then of course we can go in higher degrees, w, x, y, and z, and we can continue to do so. Now take note that since we are approaching our ball in an infinite number of directions with this, we do have to think about the path that we take to get there. So the path that we take still has to give us the same answer, which means that the limit has to exist. So if one path fails for the limit to exist, then the whole thing does not exist. However we approach it, the limit must exist. So what do I mean by that? Let's take a look at these two examples here. Now we know for our first example that if I put 1, 2, and 3 in, I just want to make sure that this doesn't become 0, and it won't. 1 times 2 times 3 is minus 1 is not going to give me 0. So what I would do then is I'd say by the quotient rule, I take the limit of the numerator separately than the denominator. And then because of the multiplication here and the power rule, I mean, there's a whole bunch of limit laws that'll allow me to just say, hey, my answer is 1 wherever I see x, 3 wherever I see z, minus 2 wherever I see y, 3 wherever I see z. And my denominator is 1 times 2 times 3, and then minus 1. And when I get totally done, I end up with a negative 3 over 5. But what allowed me to do that is first the quotient rule. So I would have done the limit as x, y, and z approach the 1, 2, and 3 of x, z squared minus y squared over z divided by the limit as x, y, and z approach the 1, 2, and 3 of the denominator. And then, of course, I would use the product rule here and the product rule here, and then the power rule on those two, and then the product rule here. So the limit laws allow me to do this, and then I was able to do a direct substitution. Now, on B, however, this is where it gets a little interesting, is that I can't put 0 in, right? If I put 0 in the denominator, I'm going to get 0 plus 0, which is 0, minus 0, which is 0, and I have 0 over 0. And we haven't learned any kind of L'Hopital shenanigation right here for this. So what we're going to do is we're going to approach 0 from different directions. So let's approach 0 using the z-axis. So we're going to approach by the z-axis, which means my y is 0 and my x is 0. So then what I have is the limit as x, y, and z approach 0, 0, 0 is going to have 0 squared for x minus 0 squared for y minus z squared over 0 squared for x plus z squared for y minus z squared. Now I'd be in one variable, so I could think about doing L'Hopitals at that point, or my usual divide both this by z squared and divide this by z squared, and then allow z to approach 0, and I end up with just 1. So that's kind of cool. Now, let's approach one of the other axes. Now, no matter how I approach this, no matter how I approach the origin, 0, 0, 0, I better get the same number. So now let's approach by the y-axis, which means I'll do x is equal to 0 and z is equal to 0. So now I have the limit as x, y, and z approaches 0, 0, 0, which is 0 squared minus y squared minus 0 squared over 0 squared plus y squared minus 0 squared. And so I end up with -1 on this one. These are not the same. I'm approaching different directions, and the rule is, however I approach, because I have an infinite number of ways of approaching, I could have approached the x as well, is that these have to be the same. These two are not the same. -1 does not equal 1. So the limit does not exist. Not because I had 0 divided by 0. It's because the path that I chose should not make a difference in terms of the limit, and it did. It made a difference. One was negative and one was positive 1. So that's why that limit does not exist. I know you're like, let's get into differentiation. And I'm going to say, okay, well, we will, but just a moment. Now, if you remember when we first learned about limits, we talked about the endpoints and what it meant if it was inclusive or non-inclusive on those endpoints and that interval, if it was an open interval or was it a closed interval. Well, we have something similar. We're going to have something called the interior and the boundary points. P naught, so a P naught, is an interior point of S if there is a disk centered at P naught that is contained completely in S. This is an interior point. P naught is called a boundary point if S, for every disk with a center at P naught with a disk delta, contains points both inside and outside of S. So this is a boundary point. This is interior, it's totally contained within whatever S I'm looking at. In this case, my disk is not completely contained in whatever set S that I'm looking at. So this is in a boundary point, and this is an interior point. Let S be a subset of R2, so we're back in XY. S is called an open set if every point S is an interior point. That means I don't have any of this. I don't have any of these points sitting out here on the boundary. It's called a closed set if I get to include these boundary points. So if I end up allowing myself to have these boundary points, kind of like the endpoints in an interval when we are looking in just the line, in an interval. Now since it makes no sense to be intervals, we're in 2 space. Let S be a subset of R2, so some subspace of R2. And this open set is like an open interval. So in other words, the endpoints were not included. And this closed set is like when we have the brackets in. So we have the open set and we have the closed set. So it's similar to what we've done before, but now we're talking about it in terms of a set in R2 and not just a bunch of numbers in just the x-axis. Now, if we include half the boundary of a disk delta ball, but not the other half, then it is neither open nor closed. So there's going to be times in which that's going to happen. Not at this moment. There's going to be times in your math, if you continue, that you're going to have neither an open nor a closed set. If part of your disk or / ball is included and the other part is not. We're going to also have some more definitions. We're going to have a connected set. If an open set S, that means everything's contained inside, is a connected set if it cannot be represented as a union of 2 or more disjoint non-empty open sets. And the set S is a region if it is open, connected, and non-empty. You're like, what? Okay. It's a connected set if I don't have a union of sets coming together, or 2 or more disjoint non-empty subsets. It's a region if it's open but connected, and it's also non-empty. Now, we only want to consider the points that are both inside the disk and also in the domain of the function, because that's going to get us to continuity, and once we know we've got continuity, then we can start talking about derivatives. So let f be a function of 2 variables, x and y, and suppose a comma b is on the boundary of the domain of f, then the limit of f of xy as xy approaches ab is L, and this is how we write it. For every epsilon greater than 0, there must be a number delta greater than 0 such that any point xy inside the domain of f and within the suitably small distance of delta of a of b. The value f of x is no more than epsilon away from L. Using these symbols, we get this. You're like, didn't we already talk about that? Yes, but not quite to this point because we didn't talk about boundary and not. We didn't talk about that. So now we're starting to include some more definitions so we can fine-tune our definition of a limit, which allows us to talk about continuity. Now in Calc 1, these are things that had to happen for Calc 1 for continuity. So for one variable where x is equal to a, for f of x, and the following 3 conditions have to be met. F of a must exist. The limit as x approaches a of f of x also must exist. And the limit as x approaches a of x must equal f of a. Now, if that's all true, on the domain of my function, assuming a is in the domain, then that is continuous. What does it mean for us in 3 space? Well, now we have to have the ordered pair has to exist. As xy approaches that ordered pair, it also has to exist, that limit has to exist. And the limit as xy approaches our ordered pair of f of x has to be f of ab, so it has to be that ordered pair. We also get some other theorems in this section. So if f of xy is continuous at x naught, y naught, and g of xy is continuous as x naught and y naught, then f of x plus f of xy plus g of xy is also continuous at that ordered pair x naught, y naught. If g is continuous at x naught and h of y is continuous at y naught, then I can think of f of xy as g of x times h of x, and it is also continuous at x naught, y naught. Let g be a function, last one, I promise. Let g be a function of two variables from the domain which is a subset. My domain is a subset of R2, and the range, my range is just R. So no, I'm not R2, it's just R. Suppose g is a continuous at some point x naught, y naught, which is in the domain. We define z naught as being that function x naught, y naught. Let f be a function that maps R to R, such that z naught is in the domain of f. And lastly, assume f is continuous at z naught, then we get the composition. So then f composed with g is continuous at x naught, y naught, as shown in the following figure. So we now have composition. So let's determine where these are continuous and explaining, of course, our answers. So first we're going to break it down to the most inside pieces. We know that x is a polynomial. We know that y is a polynomial. And polynomials in and of themselves are continuous everywhere. So the sum, of course, is continuous then. So that means that x plus y is continuous. Everywhere in the xy plane. So if we look at the natural log of k, k is continuous. This is continuous. Everywhere k is strictly greater than 0. So that means that the natural log of x plus y will be continuous everywhere in R2 such that x plus y is greater than 0. So that tells us that y is greater than negative x. That's the region in which we are continuous, is any y value that is greater than negative x. So that's my final answer. That is the region in which I am continuous for this function. Now, I did it step by step. I looked at each individual piece and then I brought it all together. So as you were thinking about how you're going to approach continuity, start with the smaller pieces like I did. First, I started with x. It's a polynomial. Y is a polynomial. They're continuous everywhere in R. X plus y is continuous everywhere in general in R2. The natural log of some number k is continuous everywhere k is greater than 0. So k happens to be x plus y. So the natural log of x plus y is that it's going to be continuous everywhere x plus y is greater than 0. So in other words, everywhere y is greater than negative x. So let's take a look at our next example. This is piecewise. And I know that students struggle with piecewise, so we'll spend a little extra time with the piecewise. So first of all, when x and y are both not equal to 0, so when x, the ordered pair ordered xy is not equal to the origin, I use this function. If it is equal to the origin, then I use this. So that tells me in general that I have continuity at this moment without any real knowledge that it looks like I'm going to have continuity everywhere. So let's take a look then. So if I don't have x and y anywhere that's equal to 0, let's just look at the denominator of this top piece. So x squared plus y squared, x squared, y. Now, if we know that x and y are both not going to be 0 together, and if it is, it equals 0, then this is positive, so x squared is going to be continuous, and it's a polynomial, same thing, polynomial. And my y squared is a polynomial. We know that these two combined, this is an x squared plus y squared, is a polynomial. And x squared plus y squared is continuous everywhere in R2. There's no problems there. So, since there's no problems there, because x squared is continuous in R and y squared is continuous in R, x squared plus y squared is continuous in R. And since two positive numbers, which is x squared plus y squared, is always greater than 0, strictly greater than 0, provided, of course, they're not equal, either one of them are equal to 0, because those are always going to be greater than 0, then we know that the denominator is always going to be greater than 0. So x squared over y, x squared plus multiplied by y, x squared plus y squared is going to be continuous. Everywhere in R2 except at 0, 0. But we have a piecewise that says if I am at 0, 0, I get 0. So this tells me if I can bring all these together, this means that this function f of x, y is continuous everywhere in R2. And that's it. Tomorrow, we'll go over this in class. And then we'll start on Tuesday into partial derivatives. Now that we've got an understanding of continuity and limits, we can start talking about derivatives.